Okay, we'll start our lecture today. Today, in fact, we'll be more learning about this logistic neuron. Okay, so again, Mitesh Kapra's lecture is what I'm using. Okay. So we'll see. In fact, most of you would have seen his website by now. Okay, I'll project that website. So he's a great teacher. Maybe we can go through his lectures here. CS 7015 deep learning course is what he is offering at IITM. Okay, so you can see his schedule and you can see his lecture videos and lecture slides, almost a complete kind of materials he has published on the net for everyone to use and get benefited. Okay, so these are some of the quiz and assignments also he has given. The standard is high, very high. Okay, so you need to work doubly hard in order to meet up these kind of challenges. But in your end, maybe in the 7th semester, with the placements nearing, okay, I think you can put 5 hours of weekly effort. Okay, that's what I'm expecting. But this material, what he is presenting here, it requires minimum 15 hours of effort. Okay, I'm not expecting that. You put 5 hours of effort per week to meet the challenges. Okay, so this is something, some material which you would like to project now. Okay, so some of you were saying that you have some kind of confusions in solving some of the problems or understanding some of the concepts. I think confusion is essential. Okay, so without confusion, you cannot come to the conclusion. So there will be some kind of confusion. There is confusion initially, but you keep trying to probe deeply, sit with the book and read. Okay, go through the video lectures again, and thereby you may gain confidence and you may be clear after some time. Okay, but confusion is essential. Okay, all students, it's essential for every student to get confused. Okay, then only it means that they are learning. Okay, in their mind is searching for the answer. Their mind is searching for the truth. Okay, so it's more like finding the truth. It is not clear to you. Okay, in fact, the highest level of truth is God. Okay, anybody who is interested in searching for God, they need to struggle really hard. Okay, the same manner, scientific truth is almost like God only. Okay, sometimes you will not be knowing anything, and you'll be struggling in your mind. You'll be searching for answers, and with your limited mind, that's very important. Okay, we all have limited mind. We can limited brain capacity. So we all struggle hard with understanding concepts. So you try to put some more effort and try to reach that level of finding the truth. There are enough material, there are enough gurus for you to help you out nowadays. Okay, the online medium is highly active, and there are people like Mitesh Kapra and all. They are really coming up with a lot of good study materials and all. Okay, we are all there to help you out. So don't get bothered or worried. Okay, so that's the message I would like to say today's class. So in fact, Andrew NG, I don't know how many of you know this guy. Okay, he has given a course on Coursera. Okay, that course is also freely available now in the net. Okay, the Stanford professor, he is a Stanford professor. Few of his lectures are connected to our material. Okay, but our entire syllabus is completely different from what he is in fact presenting. But few of the topics, few of the lectures, Perceptron, for example, maybe you can search and you can find out from his study materials too. Okay, this Stanford material. The third one, in fact, I would like to say is by Professor Viksharaj. Okay, so he's from CMU, and he's given a course, and this is a very, very difficult and very tough course. Okay, Introduction to Deep Learning. I'm not expecting you to complete this course and all, but few of the lectures, okay, maybe 3 or 4 of these lectures will be of use to you. Particularly, which I would like to suggest here is the number 1 topic. Here it is. Yeah, the first one. Okay, learning objectives, Michelot-Spitz model, neural network as a universal approximator, then training a neural network, perceptron, learning rule, and all will be of use to you. Particularly up to back propagation, you can learn from this website. And the one important point which I would like to say from this professor's website is you will gain confidence by going through some of the notebooks, okay, which I have been telling repeatedly. The notebooks are Jupyter notebooks. In the Google Colab, you can run these notebooks and you can learn some of the fundamentals of Python, fundamentals of NumPy, okay, which in fact you'll be, if you are going for a project in neural network based project, at the end of the day, you'll be evaluated based on your project. So these materials will be of use to you. Okay, YouTube URL is also given to you. Maybe if you just click it, you will see a person teaching you how to work with the Python in the notebook. Okay, some of the topics related to neural networks, Python. Okay, it may take some time, but okay, that's why I'm saying weekly 5 hours is essential. Okay, so sit with this material, but I'm telling you at the end of the day, when you complete the course, yeah, a soft computing course with a good project on machine learning related topic will boost up your resume like anything, because it's kind of at the interview board. Maybe you can talk about this. We are all information communication and big companies. Wherever you go for interview, you can talk confidently about these kind of technologies, and you can present your project comfortably before the interview board. And sometimes it may impress them, and you may be selected for a job related to machine learning in their own company. Okay, so that kind of opportunities are there. But the kind of learning materials always it's difficult. Yeah, I'm telling you, it's not easy. Little bit confusion will be there, but keep trying, keep improving. Go for this kind of video materials and search in the net. And that's the way, in fact, we have to move forward, because the future world is like that. Okay, we cannot simply sit, I don't know. Okay, I'm not, I'm a little confused, so I want to stop learning. It is not really going to help us. Okay, you have to go through and you have to fight hard and you have to search for the truth with a passion. Okay, that's essential for future learners. So we are in a different world now. We are gradually becoming more online-oriented kind of society because of COVID. It is aggravated too, and we need to keep learning and we should struggle hard to get to survive. Okay, so that's the message. Okay, for today's class before we enter into the subject. So let us try one more thing. This neural networks book also is freely available. Okay, on the net. Neural networks and deep learning. Okay, in fact, you can go through few of these chapters, first 3 chapters, and then a visual proof that neural networks can compute any function. Okay, that's something you can go through. Okay, it will be quite interesting. If you look at this particular material, you'll be seeing some nice animations also. See here, I'll project to you the animations. You will understand clearly how we are approximating a function. For example, if I change the weight here, see here what is happening in the corresponding logistic function. Clearly you can see. And then in this particular animation, you can see when the weights are changing, what's happening. So it is projecting that clearly. So the biases are changing, what's happening when you are using a sigmoidal kind of function. Okay, so this book is really a good book. Okay, if you can read it, maybe in the early morning, maybe sit with this book for maybe for an hour, read the first few chapters. You will gain a lot. All your confusions will vanish. Okay, so that's what the point I would like to say to you. So see here how it is really working. You understand. So now we proceed. I'll be using this book also for my lectures. The first 1.5 chapters, 1.5 unit of our subject. These are the basics. Okay, so we need to put a lot of effort in understanding it in a very proper framework. So that's the message. Okay, now let us proceed. The thresholding logic used by perceptron is extremely harsh. It's not the message. Because why we need to go in for a function like 1 by 1 plus exponential of minus x minus wixi plus b is what in fact we learned in the last class. I projected this to you. It's called a sigmoidal function, log sigmoidal function. Why do we need to go in for this kind of continuous function from the Boolean logics of perceptron is what the message of today's class. Let us try to understand it clearly. So for example, for this problem, let us pretend to a problem of deciding whether we like or dislike a movie. So the same idea. Okay. So there are critics rating. X1 is a critics rating. Only one input we have here, which lies between 0 and 1. It's a Boolean. Okay. 1 means critics rating is good. 0 means it's harsh. Okay. And based on that, whether we are liking that movie or not, we're going to check. The threshold is 0.5. Then W0 is equal to minus 0.5. And W1 is equal to 1 in this case. Then what happens? Then what would be the decision for a movie? Understand it? Only one input. Okay, therefore. So what happens here is, what would be the decision for a movie with a critics rating of 0.51? Definitely it's going to be like. Okay, so we have kept the bias as minus 0.5. Okay, so 1 into 0.51 we are going to give that's the input. So here it's not exactly Boolean input. It's lying between 0 and 1. Okay, between 0 and 1. You have all the values, real values. So let us take it as 0.51 input. Then 0.51 into 1, you are going to get again 0.51, which is somewhat greater than this 0.5 threshold. Okay, so then what happens? You'll be getting W0 plus W1 x1 greater than or equal to 0 is what you are testing. Okay, so W1 x1 is greater than or equal to 0.5 is what you are testing, because minus it is. So from here to here, when it goes, it becomes 0.5. So naturally 0.51 is greater than or equal to 0.5. You understand? So naturally the output is going to be 1. Now look at the second case. If I'm going to change the input from 0.51 to 0.49, what happens? So I'll be getting 0.49 is less than 0.5. So naturally output is going to become 0. So for 0.51 you get an output of 1, but for 0.549 the output is going to be 0. That's very harsh. Okay, that's the idea. So what about a movie with critic rating of 0.49? You are going to dislike it, but there is a small difference between 0.51 to 0.49. So if that is the case, we are taking a very harsh kind of a decision. So that's why we are going for a smooth function. Okay, instead of a very limiting function like this, hard limiter it is quite. This kind of function is called a hard limiter. Yeah, I told you in the last class. Okay, hard limiter function. Okay, instead of going for a function something like this, okay, this bias value like this, greater than bias, less than bias. Instead of going for this, we are going for something, a smooth function. So how do we do that? This behavior is not a characteristic of specific problem. Okay, so there will be a sudden change. That's the key point. There will be a sudden change in the decision from 0 to 1. This we don't want. Okay, so for most real-world applications, we would expect a smoother decision functions, okay, which gradually changes to 0 to 1. So you can visualize it. We are looking for something like gradually. Okay, something like that. So that's the kind of function we are expecting. We are looking for. We don't want to take very drastic or harsh decisions. Are you getting the point? Everybody, read out so far. You understand this problem? Why it is harsh? Why this decision is not harsh? Anybody have any difficulty? Balaji?
Yes, sir, I understand, sir.
You put it, got it? Okay. Yeah, that's fine. That's why I asked. I know that few of you don't have understood. See here, the input x1 is lying between 0 to 1. Any real value it can take. Okay. So for example, I am giving a critics rating of 0.5. What is the corresponding weight? 1. Okay. And there is a theta value we are given minus 0.5. Okay. Now what is the expression normally you will write? W0. Okay. For bias, always the input is 1. Okay. 1 plus W1 x1, whether it is greater than or equal to 0 is what we are checking, or otherwise I can say W1 x1 if it is greater than or equal to this bias matter. Okay, so bias we are bringing it here. So if that is the case, if this value is minus 0.5, what you are checking is W1 x1 should be greater than or equal to 0.5 is what you are checking for this problem. Okay, so x1 is what? 0.51. What is W1? It is 1. So what is your output? What is your output? For the input 0.51, what is output? For the weight W1. Oh, it will be 1 W. That's all. So naturally, what I'm trying to convey is if the critics rating is 0.51, you are liking it. But the critics rating is 0.49, you are disliking it. You understand? There is a very subtle, very small difference between 0.51 and 0.49. That's primarily because we have a very short boundary. Okay, it's a hard limiting threshold. So we don't want to give this kind of a threshold, but we want a smooth function like this. That's why we are going for a smooth function is what I'm trying to convey. Okay, are you getting the point now? A kind of a smooth function is what we are now looking for. Instead of hard limiter like this, we are looking for a smooth function. So that's where the idea of sigmoidal function comes into picture. If I draw the sigmoidal function, it looks like this. Okay, this is a function we are talking about. Okay, now look at this case. 1 by for the sigmoidal function, it's going to take a value. Now this is your input. You have give the input, take the summation. Now what I'm going to do, I'm going to take it this summation value and I'm going to pass it through a function. I'm talking about this in the last class also. So this function, instead of a threshold, it's going to be a smooth function like this. It's going to accept the summation. That summation is given like this. Are you getting the point? Including the bias. Bias is input 1 W0. This is x1, this is x2. This is W1, this is W2. Any confusion on this? Any difficulty in understanding this? Why I'm putting 1 here? Did you understand this, Varsha? Why I'm putting 1 here? Any idea? So I'm just trying to convert, okay, W1, X1, Wi, Xi, okay, plus bias. This bias I'm looking at more like a weight. So if I'm going to look at like a weight, I'm going to put it in here within the summation. I have to imagine my x1 is equal to 1. Okay, do you understand? That's why I'm doing this. So I'm trying to bring in this bias as a weight inside so that I can have one summation. You can easily code. For coding purpose, we are doing it. Okay, that's why this bias factor always you have to remember. It's more like y equal to mx plus b. Normally this b will be separate. This m will be the weights. But now what I'm trying to do is I'm trying to bring in this bias inside this loop. Okay, so for that this x value should be 1 always. I'm assuming the input is always 1. Okay, that's the idea. That's why I can write like this. Okay, so I can write entire thing as a summation. Are you getting the point, Varsha?
Yes, sir.
Yeah, you got it. Okay. Now I'm taking this entire summation and I'm passing it through this function. That function is this. Okay, now see here this value is substituted here. Are you getting the point here now? So I can separate it. This bias is now separated here, like bias it is given. Okay, but you can also take it inside the summation by putting x1 equal to 1. You understand? So that you can start from some I equal to 0 to 1 and put this is w0. Easily you can visualize that. Okay. So now we no longer see a sharp transition and around the minus omega naught. See, minus omega naught is here, and if it goes less than 0, greater than omega naught. So that is not the point here. No, it's gradual value. That's a smooth transition. In fact, you'll be seeing such a kind of transition in something called as a fuzzy logic also. Instead of having a sharp transformation like this, we will go for something like a triangular function like this, wherein you'll be talking about something called fuzzy logic. We'll learn this logic later on, but the idea is something similar. But one point that you can notice here is this entire value ranges between 0 to 1. Okay, so for some of the ratings, if I am going to get some 0.5 value, for something I'm going to get something like 0.3. So something for here it is going to be 0.8, 0.7. All those values are now possible. The threshold value is only either 0 or 1. But you have all the possibilities, ranges now. Can you imagine something about this nature of this 0 to 1 kind of a classification? What is the immediate term that comes to your mind when we are talking about something in the range of 0 to 1? Probability. Okay, the probability. So the probability is more like this. So in fact, when it is 1, you completely believe that it belongs to a particular class. When it is 0, it's completely belonging to the other class. In between means it may either belong to this class with a particular probability. For example, 0.7 is more related to 1. 0.3 is more related to 0. Okay, you understand? So you can fix some kind of a probabilistic measures for the classification. So that is the idea of sigmoidal function. Okay, so logistic function we call it. We no longer see a sharp transition, but we are seeing a smooth function. So now this is a difference. Okay, so we have seen it here already. X naught equal to 1 I have put. This is a bias. Weight also, bias is also being included here. And this is for what? It's a perceptron. And this is for sigmoidal neuron. Now we are going to call it as logistic neuron. Why it is called logistic? The transfer function what you are using is a logistic function. 1 by exponential of this value. Okay. So this is a logistic function. So it's a sigmoidal, another name. So it's a sigmoidal neuron is what we are talking about here. It's no longer sharp either 0 or 1 kind of an output. We're going to have all kinds of real values between 0 to 1. Okay. So the function is going to be like this. So between 0 to 1, we're going to have all kinds of values. So it's more like a function like this. Yeah. So this kind of function we are talking about. Between 0 to 1, you have all values. Okay. So imagine that very clearly in your mind. So now that's what we're based on the inputs, we're going to take this decision. Previously, you are taking this decision. Varsha, can you put these two in your own words? If you are interested, maybe tell. Otherwise, no problem. Anybody, just give a try. Okay, I'm not asking her alone. Just give a try. What we have been discussing so far. Just put in your own words. What is the difference between these two? What's the difference? Anybody? Gurubaran?
Sir, in the perceptron, we have a sudden change of the outputs, but in sigmoid, the input is gradually increasing, decreasing with respect to the input.
The input is not
output.
Output is going to change like. So here, here, see if I want to change the what do you call the curve? Okay, something like this now. I want to change the curve. So the change, if I want to change this curve, what do I need to do? I can change this WI. Okay, the WI consists of two parts, the weights as well as the bias. So I can change this WI and W naught, and I can adjust this curve, and thereby I can separate out. I'll be classifying my data accordingly. Okay, so let us see how we can do that. How we can adjust this. So here is the
Sir,
yeah. Basha.
sir, in perceptron, it is the outputs are 0 and 1. In
Yeah,
sigmoid, it can be between 0 and 1.
yeah,
Like
that's right. Yeah, the range.
okay, sir.
Okay, you understand that? So you
Yes,
can
sir.
see, you can normalize any output to this range. Okay, you understand that? Because between 0 to 1, you have infinite values. So you can normalize any values. In fact, you might have heard of orthonormal vectors and all. You can take any vector and you can find the unit vector of it. By taking the length of the vector and you divide by that length, any vector. You understand that? So you can convert
Yes, sir.
any vector into unit vector. Thereby, you can take any output. Okay, any output and you can normalize. So normalization is one important factor when it comes to neural network. And you are going to take a range of 0 to 1. And if this is going to be the range, and that is more like the probability. Okay, the class, whether it is belonging to a particular class or not is what you are trying to check. So the class, if it is 1, it belongs completely to the class. Or if it is belonging to 0, it belongs to completely to another class. But in between, you can fix some probability. Okay, the range can be this, you can fix. Okay, so you'll see that with some examples. But right now, just think about this. Now, this is the kind of function we are talking about. And this is a sigmoidal neuron. Okay, can you see the range? 0 to 1. So, but the key point that you have to understand it is not smooth, this function, more a discontinuous function. Okay, it's more a discontinuous function, not continuous. Okay, that's clear. Not differentiable also. So that's another one major problem. See, when you are talking about gradient descent algorithm, we are talking about derivatives. Okay, so when it comes to backpropagation algorithm and all, these derivatives are going to play an important role. So if that's what we are going to learn next, backpropagation. But the point is, this is discontinuous. This is not really advantageous. Okay, so but this function is a smooth function, and you have it is smooth, continuous, and differential. That's the advantage of log sigmoidal functions. Okay, so earlier we mentioned that a single perceptron cannot deal with this data. So this is what we learned. Okay, now is it possible now to, with the help of a sigmoid function, okay, sigmoid neuron, whether it is possible for us to train this kind of classification, train our neural network for this kind of classification is what we are trying to do now. Okay, so but we live with this error in most real world applications. The hard to drive the error to 0 in most cases, and we instead aim to reach the minimum possible error is what. So here we are classifying 3 blue points. See here. So this kind of misclassification is a problem always. But normally we will be happy with some minimal error. That's what I told you 2 classes back. With some minimal errors we will be happy. Okay, we cannot exactly get accurate classification. Normally we will be classifying with some minimal error. Okay, so this line is a very good approximation if you look at it. With the minimal errors, 3 blue points, 3 red points, classification error. But we live with this error. That's the point you need to take. With a pinch of salt, we have to take this point. So now here is the algorithm. So we have data points, okay, X and Y. So and we are going to take some initial random weights in the same manner. But here we are going to talk about something more like more number of inputs and more number of outputs. We'll be entering a domain of vector domains, vector calculus, wherein this W transpose X can be imagined to be X transpose WX. It's multivariable. Okay, we'll be talking about something more like a matrices and all. We'll learn that, but gradually just take it in your mind that this W transpose X is more like X transpose WX for multivariate keys. Multivariable keys. Okay, so the parameters in all the above cases, W is a parameter which needs to be learned from the data. The learning algorithm for the learning parameters is W. Okay, same manner, and we are going to use a gradient descent learning algorithm, and there should be some error or loss function. It can is the model clear to you? This is what we have been talking so far. Okay. So why it's called a W is a parameter, because the parameter is going to change. Okay, we are going to learn this parameter. Learning happens through this parameter, and by changing this parameter only, we are learning this particular data set. Okay, we are learning this mapping. This x I to yi mapping. We are learning through the W. These weights are being adjusted using what algorithm? Gradient descent, perceptron learning algorithm. Okay, perceptron learning algorithm is a form of gradient descent. Okay, so and then loss error function to get the. Okay. So the perceptron learning algorithm. If you look at the perceptron learning algorithm, in fact, I will be getting something like W plus X, W minus X. New weight equal to this a kind of algorithm. But in the case of gradient descent, which in fact we are going to show it again now, today's class also, more like eta dou E by dou W. This kind of logic. And this dou E by dou W, and we have derived this in fact, and we check that what is that we ended up in? W is equal to W plus learning rate times E into X, where this E is nothing but the error. Yp d minus yp. Okay, this is a desired output you are expecting, supervisory mode of learning, and this yp is a neural network output. So based on this error, we are going to adjust the weights, and this is a learning rate. And today's class also you'll see how Mitesh is approaching this particular issue. Okay, so now this is the kind of data we're talking about. The output is either 0 or 1, and then here we apply this. The parameter is W, and gradient descent. We'll see that objective loss function is more like this. Okay, the learning algorithm should aim to find a W which minimizes the above function. Okay, that's what we are aiming for. Is it clear? The problem statement. Can somebody put in words this problem statement? What are your understanding from it? Just can you explain this slide? Anybody? Bhaskar? Yashwant Bharati? Can you put in words this slide? Bharati? Put it in words. Anybody? Arun Balaji?
So we need to
You
determine.
start with this. No, you start with this. Okay, this lines. What do you are understanding? How do you put in words? This put in words. This all this 4 lines.
So we need to find the parameter W.
No. How do you understand the problem statement? What is given to you?
About the whether we like or dislike. We are given the movie. We need to find whether we like or
what
dislike.
What is the input? The movie is given to you.
Yes,
okay, and you need to check whether you like it or not. And this xi indicates the features of the movie. IMDb rating, actors, director, all those things. Okay, and output is either like or dislike. How many set of data set you have? I is equal to 1 to n.
N.
Okay, now you tell. Yeah, proceed.
So to find the parameter, we will be using the gradient descent algorithm. So first we will use the error function, and then based on the error function, we will be adding or subtracting to find the W.
That is okay. Okay, that is the gradient descent you are talking about.
Yes, sir.
Is it not? Yeah, very good. So the point is the mapping, okay, between the input and output. The functional mapping is happening through this particular function. That's very crucial. Okay, so we need to have this kind of a function now. Sorry. This kind of function. We are talking about this kind of. So this function is going to decide this mapping between the input and output data set. There is an input, there is an output. So we're going to map this now. That mapping is decided by this function, log sigmoidal function. But that log sigmoidal function is adjusted by what? The weights and biases. So we need to learn these weights and biases in such a fashion that we can classify data. For this particular type of movie, I like this. For this particular data set features, I don't like it. Okay, so this is classification, a clear classification problem, supervisory mode of learning. Because why is called supervisory mode of learning? Because it's labeled data. Data is labeled. The outputs are given to you. Okay, always remember that. Now the learning algorithm should aim to find a W and minimizes the above function. So the gradient descent rule is what we are going to see. But before that, let us take some random values of W and B and try to sketch the graph. Okay, so this is a mapping. What is this? This is the input, this is output. And this is a function that is sitting in between. Now you see for different values of weights and biases, this function is getting adjusted. Okay, so here this is the first function when the only weight is there. Okay, 0.50. So I'm getting something. The corresponding loss function is huge. What is this LWB? Can somebody help me out? This is nothing but the error. Error between what? The labeled data output Y and neural network output for your particular weights and biases. Okay, this neural network. So if you see the difference, Y cap is what? The estimated one, and YI is what? The desired output. So you can square it. When you square it automatically, you can either keep it like this, desired data minus YI cap. Both are one and the same when you square. So naturally, so this is what the error function is all about. Error function. This error function tells you what? This YI is nothing but labeled data output for the particular pattern of input. For the first pattern, maybe the pattern 1. Pattern 1 can have features like IMDb rating, actor, character, and then particular sound engineer, musician. So you fix all those values. And what is output? Y1. Okay, this is P1, it is Y. Okay, for first pattern, the output is Y1 is 1. If I'm going to say this, for all these values I will feed it to my network. For example, the IMDb rating in terms of a number. Okay, everything numerically I have to bring in. I have to bring everything numerically. Qualitative data you cannot bring in. Okay, if an actor is Matt Damon, fix a number to him. That's all. If the director is some person, you fix a number to him. So you bring the values here and you give all the inputs to the neural network. Take the summation. Okay, then pass it through your function. That function is what? This kind of function. This is what I'm doing. And if you pass it through the function, you are going to get your output. Okay, so that's a neural network output. This you call it as an estimated output. That's why this cap is there. More like a cap. This cap indicates an estimated. You are trying to estimate something. Okay, for this kind of an input, what is output? But it will not be correct. It's only it's more kind of an approximation only. It will not be perfect all this. Okay, so perfect zero error you won't get normally for most of the data. For simple toy data set you may get, but for bigger data set you will not get. Okay, now can you see it? What's happening? So this function is what we are trying to fix. So now you see, I have now taken 2 points. Okay, look at this point. Input point. 0.5, 0.2. So what is the kind of a data set we are talking about here? Single input data set. You understand? For this particular graph is for one single input, but you can also think in terms of a vector of inputs. Okay, but this is for only one input. That input in this point, what is that value? 0.5. What is the corresponding output I am expecting? 0.2. So now your curve has to pass through that. Okay, then only I can get the perfect error can be 0. Error can be minimized for that case. Okay, so anything at this point, if I'm going to see, what is the probability? Now tell me, what is the probability for this point? Okay, what is the probability that that person is liking that movie or disliking that movie? What is the probability? Can somebody tell me that value from this particular point? What does that in fact tells you? What is the probability of liking?
0.2.
Exactly, good, very good. So the output is in terms of probability now, because the output ranges between 0 to 1. The output ranges between 0 to 1 primarily because the function is sigmoidal like this. Okay, now for this particular case, I got a probability of 0.2. It means it is very close to the class 0 rather than class 1. The class 1 is here, class 0 is here. So for example, if I am going to get for this particular point something very approximate to 0.9, so then it belongs to which class? 1 class. More, it is very closer to point. Okay, if it is 0.5, it may neither belong to this class 0 nor to this class. It is in between. Okay, you understand what I'm trying to convey to you? But this curve is changing. How it is changing, Arun Balaji? I am getting different curves here. How I am getting?
As the error decreases, the curves tend to be more smoother.
No, how the curve is changing? How after all you are changing the curve?
So by changing the values of weights and bias.
Very direct, very good. Krishna, va?
Oh, sir.
Very good, very good. So by changing the bias, weights and biases, in fact, you got different curves like that. That's all. Very simple. The idea, don't get confused. It's a very simple idea. Little bit of deeply, if you start thinking, easily you can catch out of these ideas without of much difficulty. Okay, because the lecture material is so super. Okay, the slides and all what he has prepared, Mitesh Kapra, is fantastic slides. So easily you can go through, by going through the slides, you can understand the ideas comfortably. So look at this. That's what this. So this is out. This is what you're taking in. Okay, this is a sigmoidal function you are putting. And you are computing the sigmoidal function. The output is this. Okay. The function of this function is nothing but this one. This one. Okay. Suppose we train the network with xy 0.5, 0.2 and 2.5, 0.9. Okay, and the corresponding value you are seeing it here. The function is this. So this is a sigmoidal. You are getting this curve by adjusting W and B. That's all. That idea is important. So you may not be initially passing through the curve, but gradually you will reach that point. Okay, now let's go to this website. I think I'll go to this website. Here is that lecture. Okay, 1 minute. Just I'll download it. Open it. Yeah. Directly you can see all these data set are all right. This all we are seeing. Okay, we are seeing this. We are seeing this. Yeah, here comes the idea. Now look at this gradually. What's happening? Okay, this is what we are fixing. Now it has taken up a point. Okay, now we'll start with some random weights. Okay, initially he has chosen some W equal to 0.5 and B equal to 0. Look at the curve what we have obtained. What do you say about the error, man, for this case? What is the error for this case? What is the error for this case? The error will be very high. You understand, everybody? So I would like to minimize the error. What do I do? I'll go for the function, loss function. This is called the loss function. This is the loss function. Okay, so I'll be changing this. I'll be computing this loss function. Okay, yi minus fxi the whole square. You can keep it in both ways. Fx, because as you are squaring, you can keep it in both. In that slide, it is given. This is the estimation. Okay, estimation. This is the true value. True minus estimation. Okay, that's the difference. So you compute this, and you got this squared value like this for two inputs. Nah? Okay, you got two inputs. Okay, one is 0.5, another one is 2.5. Compute for both. Compute for all the squared values. So this, what is this 0.9 and 0.2 tells now? Anybody? What is this 0.9 and 0.2 tells?
Probability of the liking the movie or the output.
No. Careful. Yeah, little bit understand the idea. Go back. Okay, we are fixing something called a loss function. What is this loss function? What is this yi? What is this?
Actual value and estimated by the
actual value estimated by unit. So if that is the case, what is this yi? 0.9 tells you how many data here we have taken? How many data here we have taken? We have taken 2 data. You understand? This is a The network is like this. Only one weight W0. Okay, only one bias V. Okay, and here we have taken it as 0.5. If I give 0.5 for the given weight vector, the output should be near to something like see the output 0.2. You understand? Can you see it clearly? Y axis. That is output. So this is the label data. For 0.5, I am trying to map it with 0.2. This is X, this is Y. In order to map it, I am looking for a particular weight vector and a particular B0 vector. How I am going to get that? By summing, passing through a function. Okay, this is the basic diagram. You should remember this. So this function is nothing but 1 by 1 plus e power minus this summation. Are you seeing it clearly now? So this function, if I plot between x and y, if I'm going to plot, my data is somewhere here. It should pass through this. That's what I'm looking for. How do I get this curve? That's this curve. How this curve can be changed? By changing weights and bias. Is it all right? Are you understanding it clearly now, what I'm saying?
Yes, sir.
Yeah, now that's what I'm going to do. So now this is a 0.9. Okay. So this 0.9 is this value, output, Y1. 0.2 is output, Y2. 2.5 is the input, 0.5 is another input. That is X and Y. Okay, you understand? Between those two, I'm going to do it. Now I have computed, if I'm going to pass f equal to 2.5 the whole square, I'll be getting a huge error. So 0.07. Now I'd like to minimize the error. We want loss function to be as close as 0 to possible. Okay, so naturally we are trying to minimize it. See here, for different values of WB, I'm getting a much better result. Can you see it? So initially for the first weight, it is like this, 0.5 and 0 bias. For the second one, see, I take this weight, I take this bias, and I plug in here. I'll be getting this curve. And if I compute the error between this curve and this point, I'll be getting a huge error. That's what we computed in the previous graph. This error is 0.07. I don't want this. I want to minimize. So using a learning algorithm, I'm modifying the weight and bias. So when I modify, I get a different weight. But this is very bad. Okay, this is not a learning algorithm. In fact, randomly he has put some values. When you do it in a learning algorithm, weights at every stage will decrease. But here it has increased too much. Okay, now I'm going for a next function. This is much better. 0.07 to 0.02. The error has minimized drastically. What for particular bias and weight. Now use my intuition and choose something near to it. I use 1.42 minus 1.73. So if I see here, the intuition is if I keep increasing the bias in the negative way, the error is coming down. See, that's the idea here in this case. See, I get a much better. This blue curve, can you see it? That light blue curve. So that's next year. Now 1.78, I'm getting almost to get 0. All is 0 error. Perfectly passing through the points. So now tell me, what is the probability if I give my input as 2.5? What is the probability of this data X being in the class 1? What's the probability? If I give 2.5 as my input, so the question is clear? Yeah, this is the data. What are all the data set? Can somebody help me out? For X1, what's the X1? Is what? X1 is 0.5. What is the X2? What is X2? It is 2.5. Okay. 0.5, I'm mapping it to what? Can somebody help me out? 0.5, I'm mapping it to? Varsha? If this is X, there should be some Y. 0.5, I am mapping it to what? Gurubaran.
Sir, 0.2.
0.2, that's all, very good. 2.5, I am mapping it to 0.9.
0.9.
Okay, is it clear? So these two are two different classes. This is very near to 0, this is very near to 1. Okay, let us imagine like that. Then we'll see. Now I'm asking you, in this curve, what is the probability of x2 belonging to the class 1 point? That's what this particular expression in fact is. Okay, this particular curve is. So this is very toy data. Okay, only two inputs, only one input in fact, and only one output. You can imagine this. Okay, what's happening? The same can be scaled up for millions of inputs. Keep that in mind always. We are talking about big data. We are talking about learning in a higher dimension, not in a single dimension. Okay, we'll see that gradually. We'll understand. But let's try to put some effort in understanding this particular concept. This idea is whether it's clear to you all. Anybody having difficulty in understanding this, please ask me. I will repeat again. Anywhere you find it somewhat difficult to understand.
Sir.
Yeah.
Sir, how are we choosing the weights and biases? How to, like, what algorithm do we use?
That's what. See, for perceptron learning, we employed a very simple logic based on the cosine angle. In the last class, we see mu weight equal to w plus x, old weight equal to. Okay, so the kind of data set, in fact, we are talking about, a particular pattern is here, another pattern is here. So when I'm going to plot a line, this line satisfies the condition w transpose x equal to 0. Therefore, the weights are perpendicular to this line. That's what we learned in the last class. So these vectors, okay, if you look at these vectors, they enjoy very small angles, but with respect to the weight vector. And with respect to the weight vector, these vectors, they are going to have a large angles. So naturally, this side is negative, this side is positive, is what we learned in the last class. So naturally, we get w plus x, w minus x.
Yes,
are you clear about this in the last class?
Yes, sir. This I'm clear, sir. In this one,
this one is randomly, yes. So far, we are randomly applied. Okay.
Okay.
We have updated the weight in a random manner so far. Now, professor is introducing you the gradient descent algorithm. Okay. From what you call the Taylor series form.
Okay, sir. Have you discussed about the
the gradient descent? I have discussed about it. Okay. By directly giving you the rule, new weight is equal to old weight minus eta rho e by rho w. In fact, that's what we are going to see now. Okay, professor is approaching. This is the first order. It is a first order derivative. Okay, we can approximate any function using higher order derivatives too. That's what Taylor series is. So we are going to approximate the rho e by rho wi more like this. We'll see that. Yeah.
Okay.
So far, it's clear. Any doubts? It's randomly has applied the weights and biases. No learning rule employed. Based on intuition, he has applied it. And only to study the curve. Okay, how by changing the weights and biases, how the curve is changing. That's what we have learned this particular slide. Okay, now here you can see here, and he is studying the error curve. Okay, for some random values. For different values, see here the error is changing. So this is the error. And this is the bias. This is the bias, this is the weights. For different values of W and B, and he is studying the error, how it is changing. See here, initially the error is large, and then you will see gradually this point. Can you see this point? It is going to come down. Error is going to come down. The error is this point. Error is going to come down. You see here how it's weight. When weights are changed, error is going to come down. See it?
Sure.
Yeah. So just over this particular in fact, a plane, a line, in fact, you're going to see the one particular set of weights, the other one is equal. So the error is going to gradually come down like this.
Okay, sir.
How do you understand this? Are we talking about a plane here? No. We have only one input, one bias. It's a line. Okay. So here he has marked these points. Now, what are those points? They are the error. Okay, he is talking only about error here, not what do you call the line dividing classification. Classification is here. The classification is not a line, it's going to be a smooth sigmoidal function. Okay, you understand? Everybody with me? X and Y classification is based on this. The line is passing through this. Okay, the curve is passing through this. So we are not, no more we are talking about line. Only this is a line, primarily because bias is 0 and we are getting only one W naught X. Okay, and when we are passing it through the sigmoidal function, we are getting a line like this. But for all other values, it is sigmoidal functions. Okay. That point is clear? Did I confuse you? Or can you somebody tell that clearly again? This is not a classification curve. Okay, this curve is basically an error surface. Error surface relating error as a function of weights and bias he has plotted. So here, in fact, we are talking about how the error is decreasing for varying values of W and B, and this is the classification plan. Okay, the classification plot is either 0 or 1 kind of plot. Instead of either 0 or 1, we are going to have the range of values between 0 to 1. Probability. Okay, is it clear? Everybody with me? Any doubts? Anybody? Here comes the idea. So think about this. So initially you have the theta is the parameters W and B. I'm going to change by theta, del theta in such a fashion that my error should be minimized. So this is the kind of learning rule we are talking about. This is the weights. New weight is equal to old weight plus some beta times delta theta. Okay. What's the right delta theta to use? Now, what is delta theta here? Ananta Karthik?
Sir?
What's the delta theta?
Sir, error, sir.
No. Carefully look at this. Slide up, Baran. Change
So the
weight.
change in weight and change in weight that we say.
Delta theta. Let's say delta theta. Okay. Delta theta is change in weight. See, when I modify this weight, okay, when I modify this weight and bias, as Ananta Karthik is saying, the error will decrease. Our goal is to find out the perfect delta theta. How much I'm going to change my weight, how much I'm going to change my bias. Once I know that, then I'm clear. I know that my error will come down. The answer comes from Taylor series. Okay, and I will leave this slide. I will do one thing. Today's class, in fact, I presented the idea. Maybe by tomorrow, whether it will be feasible for you to watch one more video lecture by tonight. It will be advantageous for you. It will be difficult or openly tell. Sitting before computer again for another 30-40 minutes. All right. Okay, then I will teach. I thought of asking you guys to watch his video, okay, and go through this, and tomorrow we can have a discussion. That's what I thought. It's all right. Whether it's possible for you guys to do it.
Sir, no problem, sir. For me, no problem. I don't know.
Not everyone. Okay, if it is feasible, go through his website and his this particular lecture. His lecture, it's here. Okay, his videos are here. We are in the third unit, okay, lecture 3. This is second module, I think, video lecture. You can go through that if it's feasible.
Sir, can you put up this link in the classroom, sir?
Yeah, it is. In fact, okay, I put it in the chat. Okay. See, it's more like a flipped classroom. They are calling it nowadays. Okay, flipped classroom. You know, you watch the video and come to the class, have discussion with professor and you use the class. What happening in all foreign universities nowadays? We should also increase our standards, okay, to good level. We can compete. Only thing we should sit and learn. You guys have to put some hours, extra hours of effort. See, I have just gone through some of the undergrad level students. How much hours of effort per week they are putting in European universities and US universities, top ranking universities. A minimum 15 to 20 hours of studies, apart from the regular class hours they are putting. Okay, but here I think in India we are putting maximum 5 hours Personally, I feel we need to increase this to this 15-20 hours. I think in top universities, IIT, IITM, okay, they are putting that kind of effort. I think in Shastra, we need to raise our level to this 15-20 hours target. Okay, I think we are now in the range of 10 to 15 hours, 10 to 5 hours. We have to increase it to 15 to 20 hours. Then only we can, at undergrad level, we can compete with the IITs. Okay, that's my point. So few students are doing, but all the students I want. Okay, we need to do that. Okay, with that, I'm winding up today's class. Anything you wanted me to discuss? Okay, I'll stop here.